Hello, everyone. Thank you for the introduction. The title of my presentation today is Introducing Connection Minimality for AL Ontologies. So the problem that I would like to discuss about is called abduction, which you may already know from a couple of presentations before. And here I would like to present a day-to-day example. So suppose you are walking in the rain, then deductively you are going to get wet. And abduction is basically the reverse of it, right? So suppose your friend is coming into the room, you might start thinking to yourself, okay, maybe it is raining outside. On the one hand, deduction is sound because definitely you know that water will make you wet. But for abduction, at least what we would like to have is something that is consistent. Because it's not necessarily the case that you are wet because of the rain. Maybe it's something else, like for example, you tried to fix the water faucet in the kitchen and something went wrong and you get wet. And the solution space for this is actually could actually be big and even infinite. And for this, there are already many ways to pick which ones that are interesting via the notions of minimality, for example, subset minimality or semantic minimality, etc. But here we argue that none of them really consider the internal structure of the knowledge that you have at hand, namely the background knowledge. So for example, subset minimality is simply a property on a set. It's a mathematical property, right? So and for example, semantic minimality focuses more on the relation between different solutions. So it's still focusing on the solutions rather than taking into account more the background knowledge. So for this, because of this, here we would like to introduce the so-called connection minimality, which really accepts the solutions which connects the background knowledge and the observation. And we do it for EL, which is quite a prevalent fragment in practice. But before we get into details into how this actually works, first I would like to introduce you to the problem definition in a little bit more formal way. So suppose we have a T-box T, which does not entail some observations C1 is a C2, we would like to find a set H such that if we add H to T, then we have the entailment. Here, T simply consists of axioms. H is built from some predefined signature, so you can see this as signature restriction. And C1 is C2 is, as I said, the observation. And we represent this as the following triple. And another restriction is that we only deal with EL axioms. So for example, this one here, pizza with cheese topping is a cheesy pizza. As you can see here, we do not have negation or disjunction, which is quite nice because then for the second restriction that we already discussed before, which is consistency, this holds trivially for EL simply because of the syntactic restriction. And now we get into the example to illustrate a bit why this notion of connectedness between the background knowledge and the observation could be meaningful when you do an abduction. So suppose we have the following T-box consisting of two axioms. The first one says margarita is a pizza with mozzarella topping, and the second one says pizza with cheese topping is cheesy pizza, which is the one you saw before in the previous slides. And suppose also we have the following observation. Margarita is a cheesy pizza, which is not entailed by T. And it is not so hard to see that mozzarella topping cheese topping is actually a consistent abductive solution because see here you can replace mozzarella topping in the first axiom with cheese topping, and then you have that margarita is a pizza with cheese topping, which in turn is a cheesy pizza, and you can show the observation. However, imagine that this ontology T, this T-box T is a part of much larger T-box with many different atomic concepts, then something like this could happen. So you have in your extended T-box, you have the atomic concept country, ice cream, pizza base, pizza topping, etc. And you have the following solution, which is actually consistent. And to have an example for the minimality, this is also subset minimal. Margarita is a country is ice cream is pizza base is pizza topping, and pizza topping is cheesy pizza, which is obviously not making sense at all, right? That's obvious. Yeah, that's an obvious example. As another example, suppose, which is not quite obvious here, suppose we have the following T-box about research, doctorate, professor, about universities, which I will not explain to you in detail, but suppose we have an observation that is professor is a researcher, and this observation is not entailed by T, but you don't need to think about it. Just trust me on this. And here, professor occurs in T, so here, and researcher also occurs in T, so for example, here. And if you consider the following solution consisting of two axioms, chair is research position and PhD is diploma, it actually quite makes sense, right? It actually makes sense, yeah. And as we can also see that the first atomic concept used in it, that is chair, is actually related to professor through the third axiom here. And PhD is related to professor because professor is connected or related to doctor, and then doctor is related to PhD here. On the other hand, both research position and diploma are immediately related to researcher through the first axioms here. So far so good. But if we consider the second solution, which is also consistent, it doesn't look like it makes sense, right? So here, professor is a funds provider, and the second one is grant application is a research paper. And as you can see here, this solution uses funds provider and grant application, which occurs here, but neither of them are in some way related to professor nor researcher. So now, in order to define the minimality notion, which really reflects the example that I showed you before, we need a couple of ingredients. The first one is the so-called connecting concept. So what is this? We can first consider the following equivalence. T entails C1 is a C2 if and only if there exists a concept D such that C1 is D and D is C2 in T, right? And in this case, then we call this D is a connecting concept. And in our context, we also prefer something which is less conjunct. So for example, if the left one here, A and X or B, is a connecting concept, but the right one here with an additional C here is also a connecting concept, then we always prefer the left one. And how do we use this for abduction? So we simply find the concepts D1 and D2 such that the following holds, and then we turn D1 and D2 into connecting concepts. However, due to the problem definition, there is a restriction there which restricts us from using arbitrary D1 and D2 and making them connecting concepts. So this would lead into the second ingredient, that is description trees and homomorphism between them. So what is description tree? So suppose you have the following concept here, which is a little bit complicated, but yeah, basically the description tree is kind of like an expression tree, but you consider the atomic concepts as labels and the role restrictions here as some sort of a nesting level. So for this example, first from the topmost level, you collect the atomic concepts and put it as labels of the root node. And then whenever you see a row restrictions, you go down one level and then put a label on the H and do it again as before. You put A here, and then for each row restrictions, you go down one level, branch it and branch, and also then put the atomic concepts in the label sets. And for the homomorphism, I actually need another description tree, so I put it on the right side here, and as you can see, it's almost the same structure except the labels. And basically, homomorphism is that we mean here is something which connects the nodes such that it respects the labeling of the edge. So we start out with the root, and then whenever we find a labeled edge on the right side, you must find the similar labeled edge on the left hand side, but and then you continue down like this. So here R1 R3 R1 R3, here R1 R2 R1 R2. So this is all fine, and that's all the ingredients. And now how do we construct the solutions? So again, suppose we have the previous ones, D1 and D2, such that D1 subsumes C1 and D2 is subsumed by C2, such that we have the homomorphism. Then the way we construct H is by connecting the labels that are related by the homomorphism. And also another property is just the previous conjunct minimality that we discussed before. So back to the example, suppose the left one is D1 and the right one is D2. Then we simply look at the lines here, the purple arrows, and then connect them together. So for the root, we have L and H is E. And for the second one here, A is F. And for the third one, M is a tautology. So you can throw it away. And the last one, B, is G and K. But in case like some of the connections are already entailed by T. So for example, here, if T entails L and H is E, then you can also remove it. So that's how we construct the solution so that it satisfies our connection minimality. And yeah. So last but not least, we have introduced the connection minimality by first showing what might go wrong when you use other stuff, and then we proceed by showing our novel minimality notion. And as a future work, we would like to relate this to EL abduction technique based on prime implicate abduction technique in first-order logic, which we presented yesterday in Sophie. So we would like to show that since EL can be translated into a fragment of first-order logic, we would like to show that this connection minimality really has a deeper connection with prime implicates in first-order logic. And last but not least, we would like to have some implementation with spas. Yeah, thank you.